permission, yeah?
Yes, sir.
So we'll be starting with a very simple problem. You see that whenever we have a system, electrical, actually we need some basic laws and principles to derive the mathematical model. Similarly, if you have a mechanical system, there you need some mechanical laws just to formulate your system, okay? In most of the cases, we can make an analogy between the forcing functions or physical quantities. For example, sometimes a force in mechanical system can be made analogous as voltage. A displacement in your system can, or velocity of your system can be made analogous to the current of your electrical system. Similarly, the acceleration of your mechanical system can be similarly, the displacement of your system can be analogous to the current, okay, charge, something like this. Okay, if we derive the mathematical equation, you will see that the mathematical equation that you will have a general form, and you can fit your equations to your purpose according to the system you are dealing with. Okay. Okay, this is a simple Newton's second law. Don't you know this thing? That if we apply a force in a mass, then your mass will begin to move with a velocity, isn't it?
Yes, sir.
Yes, sir.
Okay, can you tell me that what are this same time of analogous law in your electrical engineering?
V equals to IR Ohm's law.
Is it Ohm's law? Is Ohm's law contains any derivative or something like this? Because you see that this law is simply F is equal to m rate of change of your velocity. But your Ohm's law doesn't contain this. Rather, if you have an inductance L and a current I is flowing through the inductor, then a voltage developed across the inductor, that VL is equal to L di by dt. Have you seen this equation in your electrical circuit course?
Yes, sir.
So mathematically, these two equations has the similar nature. Similarly, if you have a capacitor, your current flowing through the capacitor will be equal to rate of change of voltage across the capacitor. Okay, all these three equations actually has similar form. But actually, these again physically, these three equations actually never work in practice. The reason is very simple. Actually, you know that if we have this equation with us, F equal to m dv by dt, and if you want to calculate the velocity, we are assuming that your mass was at a rest at time t equal to 0, and at time t equal to 0, F force F has been applied to the mass. Then you can easily calculate the velocity. Your velocity would be equal to what? F divided by m into t, isn't it? If we integrate equation 1, is it okay?
Yes, sir. Yes, sir.
Similarly, if we integrate equation 2, you will see that your current would be equal to VL divided by L into T. Similarly, in the case of capacitor, if we integrate it, then voltage across the capacitor would be equal to IC divided by C into T. For T is greater than equal to 0. If we plot all these three equations, how they will look like? You will see that your velocity, if you plot time with velocity, you will see that your velocity is increasing indefinitely with time, linearly. Similarly, your current through the inductor, IL, is also increasing in this way linearly. Your voltage across your capacitor is also increasing linearly. Okay? That will never happen in practice. The reason is that if you just keep, even if you withdraw your force at some point, what will happen? You, for example, at a particular point, if you are withdrawing your force, it will attain a constant velocity, and that velocity will be there in your system going on. So this cannot happen in practice. For this reason, actually, we will never find any system that will not contain any friction in mechanical system. We will not have any inductance that will not contain any resistance. Similarly, we will not have any capacitor that will not contain any what? Resistance. Okay. So if all these things are present there with some sort of friction, resistance, actually what is the nature of the friction?
It works
Fri-
against the applied force.
yeah, it will consume some of the applied force, isn't it?
Yes, sir.
And that force is lost in the form of heat or something like this, isn't it? As a result, what will happen? In course of time, some energy will be lost in friction. Similarly, if you have a resistance, then some power will be lost in your resistance. As a result, what will happen? Your velocity, your current, or your voltage will never grow indefinitely with time. Rather, it will be determined by the friction or by the resistance present in your circuit. Okay. If we can model our system gradually in this way from an ideal case to a practical case, then what usually we'll obtain, we'll obtain some sort of differential equation, isn't it?
Yes, sir.
Okay, if we want to, okay, all these are the general description in your book. You try to read out, you will understand it very carefully. This example is there a parachute example. For example, if a person is simply going down from by using a parachute, then what will happen? Due to his mass, a downward force will be acting, and as he is moving down, an air force will be acting upward as air friction, and eventually a net force will be there in the body, and that will create some acceleration. Then you can easily solve and derive the equation, and it will take the form of a differential equation. This equation has been derived in your book, and this is not that equation. I will not be discussing this equation to you. We will rather derive the equations for our case of electrical engineering. Then we will proceed with the solution. You see that the equation that you are seeing in this slide and the equation that we are going to derive for our electrical systems, mathematically they are same. And the solution is there. And I will not talk about this solution when I will be dealing with our electrical system. At that point, we'll refer this solution, inshallah. So this is what our simple electrical system that we can have. Actually, the thing is that sometimes we designate our electrical system by deriving the differential equation, and by examining the order of the derivative of the differential equation, we can define the order of our system. And I hope in your electrical circuit course 2, you have been introduced with your transient analysis of first order and second order electrical circuit. Usually the thing is that you have already understood that if we don't have any energy storage element in our electrical circuit, or if we do not have any mass in our mechanical system, the derivative term will never come. So a derivative term or differential equation will result if your system will contain some energy storage elements. Okay. In the mechanical case, your mass is the energy storage element that can store energy in the form of if it is in movement, then it will be kinetic energy half mv square. And if it is static, then due to the position, it will have some energy in it. We call it potential energy. Don't you know this?
Yes, sir.
Okay, then what will happen? If we have an inductor and capacitor in our circuit, we know that inductor ideally or ideally a capacitor will not consume energy, rather they will store energy in it. Your inductor will store energy in the form of magnetic field, and your capacitor will store energy in it in the form of
Electrical field.
Yes, that you know that the energy for inductance is simply you can write half Li square. In the case of capacitor, it is half CV square, isn't it?
Yes, sir.
So these are the equations you are seeing it from the intermediate level. But when we are dealing with, for example, some time behavior, actually you see that in your transient analysis, you have seen that whenever a system is at rest, it will have some situation prevailing inside it. But whenever some change is occurring in your system, then your system will be accommodating the change, and it will take some time to accommodate that change. As a result, the response of your system, the output of your system will have predominantly two regions. Okay, one is called transient region. Transient region is the region over which a change is being accommodated by your system. And when your change is totally accommodated, then you will have the second state appearing. We call it steady state, isn't it?
Yes, sir.
So you have your steady state and transient state in your electrical system. Not only in electrical system, whenever you are dealing with a system of the same type, all these things will be there. For instance, say you have a fan installed at the ceiling of your room. And when it is at rest, it is rest. Okay. When you are switching on, then what will happen? Your fan will begin to rotate. Will it rotate instantly to its desired speed?
No, no, sir.
What will happen? It will gradually speed up, isn't it?
Yes, sir.
And you will see that if you not change the setting of the regulator of your fan, then your fan will attain a constant speed. And as long as your voltage is same, your fan will be rotating with a constant speed. But whenever you want to change the speed to a lower level, what you will do? You will just change the setting of your regulator. Then your fan will be rotating in a lower speed. But will it just come to the lower speed instantly?
No, sir. It will gradually come.
It will gradually come. So why this change is there actually? You know that your fan contains a rotating mass, and that mass changes, stores some energy when it is in the previous state. In order to balance the energy for the next state, it will need some time. Okay, for this reason, actually, this situation will be the instantaneous change cannot be accommodated in an energy storage element. That is usually in the mechanical case, in your elementary level, we call this thing as an inertia, isn't it? It
Yes,
will
sir.
have an inertia. That inertia can be, in the mechanical case, your inertia can be due to the motion, or your inertia can be due to the rest. When it is rest, it will take some time to speed up. And when it is in motion, it will take some time to go to the next state. Okay. So if those things are there present in your system, then the input output relationship should be derived in terms of differential equation. And that differential equation solution will give you the total behavior of your system that will contain both your steady state and transient state of your system. Okay. Now, let us come to the electrical system. You are seeing this slide having 6 figures there. You see that in the left side, you have your capacitors only. In the right side, you have your inductor. Why we are doing this thing? Actually, not always that your system will have a simple RC or an RL circuit. Rather, your system can have a complicated network, and you can represent that network by N. In this case, you see that we are representing this part by N. Okay, if this N is there, that says that N is actually a network that contains some sources or some other passive elements. There is no any other, for example, there may be some active element, but no energy storage elements are there in N. Then what will happen? By using a basic electrical circuit theory, this part of the network can be represented by what? A Thevenin equivalent, isn't it?
Yes, sir.
Similarly, this part of the network can be represented by what? A Thevenin equivalent, or equivalently by a Norton equivalent. So once you have your system transferred into Thevenin equivalent, you will see that it will be a simple network. You cannot imagine more simpler network than this. Okay, you will have a resistance, we call it Thevenin resistance. A voltage will be there, the Thevenin voltage. then the capacitor that was present there in your circuit is there. Okay, same thing is there for your inductor. Now, if we identify our output that we want to know the voltage across the capacitor as our output or current through the inductor as our output, then you can easily derive the equation input-output relationship with the help of Kirchhoff's voltage law applied to this network. This is what the equation for your capacitive case. This is what the equation for your inductive case. I hope you can derive it and try to verify it and derive it. Okay. So this is the equation. This is another equation. If we go to the Norton equivalent, then the corresponding equation will be this. Okay, this needs only first year knowledge to derive this equation. Okay. Now, once these equations are available with us, can you tell me that mathematically are these four equations different?
Sir, they are similar.
They are similar, exactly. They are similar, and you can put this equation. You can put this equation into a general form, something like that: dy by dt plus, for example, say ay is equal to bx or something like this. Can we put that equation into a general form? All these four equations.
Yes, sir.
So, what is it actually? Is it not a first order ordinary differential equation?
Yes, sir.
And I hope you can solve this equation by your own. Okay. If you can solve this equation, then you will find how your y the output is changing. In this case, if you have your capacitor for Thevenin equivalent, then you will see that how capacitor voltage is changing with time. If you have your inductor, then you can find how inductance current is changing with time. And similarly, for the Norton equivalent, you can easily do this. Our objective is what? Once we have our equation available with us, actually for this type of equation, we do not need any numerical method because the solution can easily be obtained by analytical technique. Actually, whenever numerical method is introduced, we usually start with a known problem whose analytic solution is also available. The reason is that we have to compare our numerical solution with the analytic solution. If analytic solution is not available completely, then we'll have some other technique to identify whether our numerical solution is usable or not usable. Okay. Now this part I am just leaving to you for your self-reading, but I will be referring this thing with the I am just simply showing this thing to you, but later I will be using our whiteboard to just explain the thing to you. Just and we will always refer our electrical example. Then we'll be coming to this slide afterward. Okay, so with this thing, let me stop the sharing. But try to remember this graph. Okay, in this graph, you see that you have a graph. We are calling it exact analytic solution. That solution is plotted when analytic by solving the differential equation. Okay, and the upper curve with black dots. These are the approximate solution obtained by simple intuitive numerical approaches. And you will see that these two solutions is actually never coincide exactly. There exists some discrepancies between them, and that discrepancy has some limit. We have some criteria by which we need to identify that whether the approximate solution will be usable for us or not. So with this thing, I will be stopping this sharing. That let us start our whiteboard to illustrate the same scenario with the help of our electrical engineering problem. Okay. Can you see this?
Yes, sir.
Okay. So let us start with the same problem of simple, for example, say Thevenin equivalent, the VTAs. and you will have an RTH there. Then an inductance is there. Your inductance current I is our output. Okay, and we have seen that the relationship is simply can be derived as what? Di divided by dt plus RTH divided by L into I is equal to VTH divided by L. Wasn't it the equation? Okay. Then you can find, for example, rearrange this equation in this way. Di divided by dt is equal to H divided by L minus RTH divided by L into I. Okay. And you have already seen that the analytical solution of this equation. Now, a few things we have to just assume first. Okay, in this case, we are assuming that your inductance L was not carrying any initial current in it. Okay, but when inductance will be carrying an initial current in it, then this problem will be left to you to be modified, that how that initial value can be incorporated into the solution. Okay, you have to derive it by your own. Okay, then analytical. So what is the analytical solution for current? Can you remember? Your I equal to what? Your I would be equal to VTH divided by RTH into 1 minus e to the power minus RTH divided by L into T, isn't it?
Yes, sir.
Yes, sir.
So your analytical solution is available to you, okay? Why we need this? We need this because when we are developing some approximate solution of this equation, then we can compare our solution with this analytical result, okay? So let us start with how we can formulate intuitively the analytical solution. Actually, the thing is that this is actually a differential equation. If you want to solve it, then we have to integrate it. Integrate means what? You have to add some value up in such a way that your solution can be obtained. Okay, let us start with it. Okay, if we plot this equation generally, okay, when your values of L, VTH and RTH will be available, then you can easily plot this current. Your current will take this shape, isn't it? And at the steady state, the value will be VTH divided by RTH, isn't it?
Yes, sir.
Yes, sir.
Okay, then what will happen? Actually, this rate of change, in which region that rate of change is active? Actually, in this
The
region,
transient residue.
okay, in this transient region, for example, in this region, this rate of change exists. This rate of change is nothing but the slope of your curve in this region, isn't it?
Yes, sir.
If it is the slope of your curve in this region, then what you can do? You can select, for example, two time instant. For example, say this is your one time. This time is say Ti, and you have say another time there. That time is say Ti plus 1. And the corresponding value of your current is say this current is I, and this current is say I plus 1. Then what will happen? Although this portion actually is a curve, but if this distance, for example, Ti plus 1 minus Ti, we are calling it del T, and it is actually in numerical jargon, we call it a step size. Okay, we call it
Step
what?
size.
Step size. The step size of your independent variable. Then if that step size is sufficiently small, then this portion can be thought as an straight line, isn't it?
Yes, sir.
We can approximate it as a straight line. So if we just enlarge this plot in this region, you will see that you have your two time there. This is one, this is another time, Ti plus 1. And you have your current there, 1, that current is I. Another current is there, that current is I plus 1. And this is actually something like this. It will form a triangle, right angle triangle, isn't it?
Yes, sir.
Then we can we calculate the slope at this point using some simple trigonometric law? Then
Yes,
your slope would be equal to what? Your slope would be equal to I plus 1 minus
minus
I
I
divided by
del
del
t.
t, isn't it? Where
Yes,
del t equal to this. So this can be thought as del I divided by del t, and an approximation for the derivative at the point I. And when you limit, for example, will be tending to 0, then your del I divided by del t will lead to this continuous derivative di by dt. Have not you learned this thing in your intermediate level when you have been introduced with differentiation in your calculus?
yes, sir.
How to find the differentiation? So is this is very complicated something? It's
No, sir.
simple something that we are using by using our simple geometrical concept. So now the thing is that once that approximation is available with us, then our equation that was continuous di divided by dt is equal to VTH divided by L into 1 minus Ri RTSI. We can easily, okay, this is actually, this is what? This equation, this is the slope. This is the slope of your curve, okay? And we approximated that derivative in our case by using an approximation that I plus 1 minus II divided by del t is equal to then VTH divided by RTH 1 minus, then now you see that you have an I there, then what I should use? Usually, if we have an explicit algorithm means what? In that algorithm, you will have your unknown in one side and you have your known quantity in other side. That means you can completely calculate the unknown values with the help of known values. So this is your explicit type algorithm. In this case, we are assuming that our previous values I will be known to us, and we need to calculate the next value I plus 1. If we solve it for I plus 1, then I plus 1 is equal to what? I plus VTH divided by RTH into 1 minus R into II multiplied by del t, isn't it?
Yes, sir.
Okay. Now what is the seed? Your seed equation will be the I0, II. If your II is available, then what we are actually, this equation is saying that, okay, is it not the slope at the point I? Because
Yes,
this
sir.
is the
Yes.
slope. So what generally then what you can write that you have seen in your last slide, slide number 14, that your new value equal to what? Old value plus
Slope into
slope,
time. Slope into steps.
slope
Step.
into a step size. Is that clear?
Yes, sir.
Then you see that they derive the thing by using their mechanical example, but we are driving the same thing by using our electrical analog, okay? Now with the help of this equation, you can proceed with calculating the thing, okay? Then where to start? You can start with 0 time, that in this case, your index I would be equal to 0. That means if your I0 value is available, then you can calculate the next value by adding with it the slope with your step size. In this way, you can do that. So now you can easily draw the curve that you have seen there. Once your value will be available to you, then you can plot it numerically. But just for your explanation, we can write it in this way. So this is our say exact curve. If this is our exact curve, then we need to find the approximated curve, okay? So what is happening there, you see that in the approximated curve, Let us consider that in our case, your I0 equal to 0 ampere. That means at time t equal to 0, your current is 0. So we are starting from the 0. Then next, what are next thing will be equal to what? Your I1. Your I1 would be equal to I0 plus slope of this equation multiplied by del t, isn't it? So you are adding something. This is your point 1. You are adding something, for example, this thing with it, then you will be getting this point. Okay. Similarly, in the next step, you are adding something there. In the next step, you are adding something. Your next step, you are adding something. In this way, if we just continuously, for example, draw this curve, you will see that this curve is actually the approximate solution. You can easily draw this curve once your values will be available to you. Okay, let us start with a simple what we call example. Okay, consider that your VTS is equal to 10 volt. Your RTS is equal to 5 ohm. Your L is equal to say 1 Henry. Okay. And you say we assume that I0 equal to 0 ampere. And your step size del t is equal to say 0.01 second. So what is the value of I1? Okay, in this class, what you need to do, I don't know what are you doing in the other end, but what I have talked earlier, that fairness is very important in gathering knowledge, okay? And you have to be very careful about you invested money and time to acquire the knowledge. If you feel that your engagement to the other end is not being seen by your teacher in whatever you are doing, then ultimate consequences that you have there will be with you. So that you have to be very careful about. So you can, if you have a calculator, can you calculate I1?
Sir, 0.02.
How?
Sir, the voltage, sir, is VTH 10 volt.
VTH is 10 volt, yes. Then you see that your I0 equal to 0 plus your VTH is equal to 10 and your RTS is equal to 5 ohm. Then this is, hey, is this equation correct? Is this equation correct?
No, sir, it should be L, VTH by L.
Yeah, this should be L, okay? So your L equal to 1, then it 1 minus RTS is equal to 5, and your I0 value equal to 0 multiplied by 0.01 equal to what?
Sir, it equals to 0.1.
Equal to 0.1 ampere, isn't it?
Yes, sir.
Okay, so if you want to calculate the next value I2, your I2 would be equal to what? Your next value means new value.
0.15.
Okay, then old value is equal to 1 plus your VTH divided by, this is your 10. And in this case, 1 minus R equal to 5. Now your current value equal to 0.1 multiplied by multiplied by 0.01, isn't it?
Yes, sir.
And equal to what?
Sir, 0.15.
0.15, okay. So in this, you see that you started from 0. Next, your current is 1 ampere. You are getting gradually, is it not increasing?
Yes, sir.
So you can keep continuing in calculating this thing, and you can easily plot these two curves. One is analytical and another is approximated value. Then you can easily compare these two methods. This, although we will be going gradually to the specific method with more elaborate discussion, but this algorithm that is very simple, and we derived it from the very basic concept of our derivative approximation, is also we call it Euler algorithm, Euler method. Okay. Now, one thing we have to be very careful about, later we will see that a single mathematical technique may not be applicable, numerical technique may not be applicable for all types of problem. There exist many other issues to be considered, okay? So with this thing, you can easily, okay, you can extend this problem, okay, I will be left this thing with you just to consider, okay, consider that now your I0 equal to, consider that your I0 is not equal to 0, your I0 equal to say 0.1 ampere. Then you solve the same problem, both your analytical and numerical, and compare it. Now we see that when we used to compare the result, actually you see that we have an equation available for this type of problem that we obtained from analytical method. The solution, that analytical solution is actually the exact solution. Then if for a particular time instant, if we calculate the current by using the analytical equation, we can call it the actual value of your current. And we are using, for example, our approximation by using numerical technique. We can calculate another current I, say this current is say numerical IN. Then there will always be a difference between these two currents. This is what the error. That error is expressed in many different ways. This can be positive or this can be negative, or we can easily calculate the absolute value of the error. If we calculate, for example, this error in this way, IN, sometimes we calculate it in percentage by dividing it by IA with 100. This will be the absolute percentage of error. That will be the percentage of true error, because this is the true value. And when we use, for example, this absolute value, then we will call it absolute true error. In each stage, you can easily calculate the absolute value of your error, and you can also plot it with respect to your time step. Then you can easily examine that how your error is moving as your time is progressing, okay, whether it is decreasing or increasing or gradually dying out or something like this, okay. So in this problem, when you are solving, you can easily plot another graph where you will plot, for example, the error with respect to time step. We'll discuss more about error afterwards. So you see that the thing that we have already discussed is there, okay? In this case, your problem is mechanical, but in our case, our problem was a simple, well-known electrical problem, okay? This is your inductance case I illustrated. You can extend this case for your capacitor or even for other electrical circuit that have the same format. So the other things are energy balance, something we will not be discussing much about it. The reason is that these are the simple thing you have no need from your very earlier levels that try to solve it, okay. We usually, what will happen, you see, when we will be just giving lecture, so apart from, in addition to using this slide, I will also be using the PDF from of your book, okay. But in the next class, I will be showing this thing to you, and we will gradually move further. So meanwhile, what you can do, you can have your self-reading, okay. Try to collect that book and make your self-reading, because we will not consider chapter 2. Chapter 2 is a description of the software or something like this, or programming software. Many of the things we do with you from the very basic level. You try to go through it as a self-reading. Then in the next class, we will be starting with chapter 3, approximations and round of errors. That is very, very important for us in numerical technique, okay. Although you have some introduction with it, as you have already attended at least 2 courses, okay. One is your digital electronics, another is what? digital electronics and where, for example, probably digital electronics and programming, okay? Where you are programming something, what programming language you have used so far?
Sir, C programming, MATLAB, and Python.
C programming, MATLAB and Python. That means you have your everything with you, okay? So you see that whenever we using programming, actually the thing is that few things should be known to us. One is very important that you have to understand how calculation or numbers are handled by your digital computer, okay? How the integer numbers are stored in your computer, and how a floating point number. Do you know what do you mean by floating point number?
Yes, sir.
What is this?
Sir, it can have fractions.
It can have fraction. Okay, it is the definition. Why it is called floating point? Float means it is floating. Okay, that means suspending or something. Okay, something floating. Why it is called floating? Okay, you may have, because the thing is that actually I asked similar questions to the computer graduates earlier. They could not satisfy me. Although I am not an engineer or something like that, I have very small knowledge in it. Although I am still learning, but I will try to give you some introduction how we can proceed with it. Okay, you have, because this thing is very important. No matter how powerful your computer is, every computer has some limitations. Okay, it cannot process numbers smaller than some number, even it cannot process some number greater than some number, isn't it? For this reason, you see that whenever you are programming, you have to avoid two things. One is called underflow, another is called overflow of numbers. Did you ever encounter these two errors while programming?
No, sir, not yet, sir.
Not yet. Okay. But then I am introducing these two terms to you. Try to proceed with. So with this thing, I will not be starting the new topic. Inshallah, in the next class, we'll be starting the new topic. In this weekend, probably I will try to finish my lecture plan. Then once it is ready, I will supply it to you, inshallah. Meanwhile, you try to access your LMS, and I will be testing the LMS by using a Save Exam Browser. And let me give some time to prepare on it. Thank you very much. Okay, then I am giving you percentage now.
Sir, can I ask you a question, sir?
Of course.
Sir, so if we have to draw the approximation curve, so how many points do you have to consider, sir?
How many points you have to consider? This is very good point, actually. The thing is that I did not discuss about it, but
Yes, sir.
I assume that you might have some experience on it when you have been introduced with drawing curves first time in your life. That if you have a graph and graph paper and a function is given to you, your teacher is asking you to draw a plot, then what criteria you used in your earlier level just to draw the plot? Then from this point, I will discuss and answer your question.
Okay, sir. Thank you.
Can you tell me?
Yes, sir.
Can you tell me that, okay, that when you have been asked to draw a plot in your earlier very basic level, then what thing that you need to know first in order to draw the plot? Understand my question? For example,
yes,
say you have been asked to draw a plot y equal to fx, okay? Say this
Yes,
is your x, this is your y. Then what particular thing you have to know first in order to plot this graph? For example, say you have been asked to plot, say, y equal to, say, 2x square plus 2.
Yes, sir.
That means this definition is actually very vague, okay? Your teacher might have asked you, you plot this curve for x is less than equal to 0 to less than equal to, say, 2, isn't it?
Yes, sir. So condition, so there will be conditions.
Yeah, you can
conditions
plot it.
should
Now
not-
the
must be
condition is you have to plot between 0 to 2. If
Yes,
you
sir.
want to plot between 0 to 2, now your question is how many points you have to take between 0 to 2, isn't it?
Yes, sir.
Okay. Then
So I think
actually the thing is that as many theoretically as many as point you can include, then your curve will be very near to the actual one, isn't it?
yes, sir. The more points we will
More
use, it will
point,
be
yeah.
more
The
accurate.
more point you will use, then your curve will be going closer to your actual curve, isn't it?
Yes, sir.
But this is theoretically correct. When we are using computer, there exist many other issues that I will be discussing later. But in this
Yes,
case, what you need to do, we have used some thumb rule. In the
Yes, sir.
case, in this case, the problem is very simple. It will, that problem that I am discussing will not occur. But in the case of our electrical system, something like this, that contains a term e to the power minus, say, R divided by LT, something like this, isn't it?
Yes, sir.
If we have this term, we have a characteristic factor here. Because you have to plot in such a way that that characteristic factor will be depicted clearly in your curve. In such cases, you see that we have a characteristic time there. That characteristic time is R divided by L. Do you know what is the name of this quantity?
It's R divided by,
Huh?
no, sir.
No.
I don't
Time
know.
constant.
This is called time constant, isn't it?
Yes, sir.
Yes, sir.
So your time constant will give you an idea how to set your, for example, time step. If your time constant is 1 second, then what you can do, okay? Your time constant is usually drawn in such a way that you draw a tangent there in such a way, it will dissect somewhere. Then this time can be a tangent. You can easily plot it, okay? You see that when your R by T is equal to L by R, this equation will be 1 minus U to the power minus 1 is equal to what? E to the power minus 1 equal to what? A 1 minus e to the power minus 1 equal to what? Calculator नहीं आते हैं? This is equal to
Sir,
0.63.
0.63.
632. That means whenever something, if you have this equation with us, then when your current is increasing, your time constant is that time at which your current will reach at a value equal to 63.2% of your maximum value. You got my point?
Yes, sir.
And what you can do if you want
Yes,
to,
sir.
okay, in the steady state, time step is not important. But in this region, time is important, okay? If you are, well, you want to plot, for example, say 2 time constant, say this region would be equal to 2L divided by R, then you can set your value of del T such that you can calculate 10 points, for example, within 1 time constant. You got the point? In this way, you can easily set what will be the value of your step size. But this is very simple method, okay? I would say, because there exist many other issues in selecting our time constant step size. Okay, inshallah, we will be discussing when we will be discussing with error and round the gap in chapter 3. That's it from my part today. Stop recording, please.